In this video, we're going to cover section 2.4, which are applications of uninhibited and limited growth models. So application problems involving exponential growth and the logistic model, which is a limited growth model. So our objectives here: find functions that satisfy the equation derivative of p with respect to t equals k times p. That's just the derivative form of these types of functions we're going to be looking at. And solve application problems using exponential growth and limited growth. So most of these problems in this section are word problems. All right, we're going to start here with theorem 9. This says a function y equals f of x satisfies the equation dy dx equals a constant k times y, or same thing just in a different notation, f prime of x, so the derivative of the function x with respect to x, equals a constant times the function. Here they're saying the derivative of the function y with respect to x equals a constant times the function y. So they mean the same thing. So that is true if and only if y, the function, equals a different constant c times e to the power of kx. So this constant k right here in this form of the equation is the coefficient of the x within the exponent of the function. Equivalently, y, remember, is the same as f of x. So you could just use f of x instead of y equals the constant times e to the power of kx. Again, the exponent kx, this value of k coming from this form. Right? C is also a constant, but it's a different constant. We'll talk about what that means here in just a second. All right, so our first example gives us the general form, and they want you to find the function that satisfies this equation. So they're saying that the derivative of the function a with respect to t equals 5 times a. So this 5 is the k that we talked about in the last slide. So by theorem 9, we could write our function as a, the function is a, equals a different constant c e to the 5t, right? The independent variable here being t. Or you could write a of t equals a constant c e to the 5t, knowing that this coefficient of the function in this form is your coefficient of t in the exponent here, and the variable involved in the exponent is indicated in this denominator, or inside the parentheses if you're given function notation. All right, so another example, find the general form of the function that satisfies this equation. Derivative of n with respect to t equals k times n. So our function name is n, and our variable is t. So we could write n equals c e to the kt, or n of t equals c e to the kt, where c would be any arbitrary constant. Again, the coefficient of n being the exponent on the independent variable t. And notice here, the reason that this gets you back to the function, if you're given the derivative form, if you were to have this function and you took the derivative, n prime of t, the constant c would stay. The derivative of e to the kt is itself e to the kt times the derivative of the exponent, which would just be k. So the c would stay as the constant in front of the whole thing. E to the kt times k is then the derivative. So notice this is k right here, and this c e to the kt is the function n. So you could get back to the derivative of n with respect to t, or n prime, equaling kn. All right, uninhibited growth, population growth. This is one of the main applications we use this model for. All right, so our equation, derivative of p with respect to t equals kp, or p prime of t equals k times p of t, is the basic model of uninhibited or unrestrained population growth, whether the population is comprised of humans, bacteria in a culture, or dollars invested with interest compounded continuously. So in other words, there's no bound on how big the amount can get, uninhibited growth. All right, so our basic model, as we just talked about from this equation, our function looks like this. P of t, the function they're calling p here, of the variable t. They use t here a lot of times instead of x because in these applications that independent variable represents time. So P of t equals a constant constant c times e to the power kt. Or sometimes they will substitute in place of c this notation p sub 0 or p naught. E to the kt, where that value of that constant or that p sub 0 is what we consider the initial population. In other words, the beginning amount, how much you had at the very beginning. And then t is time. All right, so our next example says, suppose that an amount P naught or P sub 0 in dollars is invested in a savings account where the interest is compounded continuously at 7% per year. That is, the balance grows at a rate given by the dp over dt equals 7% is your growth rate. That's the 0.07p. So that's how this scenario translates into this model. The growth rate is this coefficient of p here. We want to find a function that satisfies the equation and write it in terms of P naught and 0.07, just like we did in the last couple examples. Then, using our model, suppose that $10,000 is invested. What would the balance be after 1 year? So $10,000 would be your P naught, your initial value. And then if $10,000 is invested, how fast is the balance growing at t equals 1 year? So a rate at which it's growing means we're going to be asked to find a derivative. All right, so P of t would equal c or P naught e to the power 0.07t based on our model. That was just like the first couple examples that we had done. P of 1, so after 1 year, we said find the amount, and we invested $10,000, so that's the P naught value is 10,000, and we're going to plug 1 in for t. So we have 10,000 e to the power 0.07 times 1. Then using our calculator, we should be able to evaluate that. So this e to the power of 0.07 should give you this on your calculator. Then you're going to multiply that by 10,000. You should get $10,725.08. We always round money to the nearest cent unless it states otherwise. And then part C, here's our model. P of t equals 10,000 e to the power 0.07t. It wants to know how fast it's growing. So our derivative would be the 10,000 constant would stay. We'd have the e to the 0.07t, right, itself times the derivative of the exponent is where this 0.07 comes from. So 10,000 times the 0.07 is 700 e to the 0.07t. So at 1 year, at time 1, the rate at which it's growing is the derivative evaluated when t is 1. So we found our derivative function. Now we're just going to plug 1 in for t and then evaluate that using your calculator. You should get 750.76, which means at t equals 1, the balance is growing at a rate of about $750.76 per year. So any rate of change is represented by the derivative of our function. All right, we'll do another example. Example 3 says the world population was approximately 6.0400 billion at the beginning of 2000. It has been estimated that the population is growing exponentially at a rate of 0.016, which is equivalent to 1.6% per year. Thus, derivative of population p with respect to t can be modeled by this equation equals 0.016p. That's the growth rate as a decimal, is the k here, where t is the time in years after 2000. So we have to consider 2000 was the beginning of where this data was collected. All right, so for part A, we need to find the function that satisfies the equation, assuming that the initial population P naught is 6.0400 and our K value or growth rate is the 0.016. And our unit will be in billions. So estimate the world population at the beginning of 2020, meaning if our initial population was found in 2000, right? If we're in 2020, that means time value would be 20 years. So that's a t-value of 20. Then find the rate of change, meaning the derivative of the population at the beginning of 2020. So basically just like we did on our last example here, just using population as our context instead of money. All right, so population at time t equals 6.0400 e to the 0.016 t, our growth rate being the coefficient of t here, and the initial value in the year 2000 being our p naught, or p sub 0 value. So to estimate it in the year 2020, assuming that the year 2000 was 0, if we're in the year 2020, that means that the t value is 20, plugging in 20 in for the t. And then using your calculator to simplify that, you should get 8.3179. And again, our unit is billion. And then the rate at which it's growing is the derivative of this function right here, p prime of t. So it's this constant stays, e to this power, all that stays put first, and then you multiply by the derivative of the exponent, which is just that 0.016. So 0.016 times 6.0400 is this 0.09664, and then you still have your e to the 0.016t. So in the year 2020, if we evaluate our derivative function by plugging in our t value of 20 and simplify that, we get 0.133. Meaning that the rate of growth of the population at the beginning of 2020 is roughly 133 million people per year. And this is, remember this unit is billion, right? So they've converted that into million. All right, so our next example moves to models of limited growth. So in other words, where the maximum value that you could end up with has a cap, right? It can't just go on forever. So we're going to use what we call the logistic equation, which is this. P of t equals L divided by 1 plus C e to the negative L kt, k and L both must be positive constants, is one model for population growth in which there are factors preventing the population from exceeding some limiting value L. In other words, this L value is the max it could possibly get. Maybe that means a limitation on food, living space, or other natural resources. K is still your growth rate. And notice in the exponent here, it's negative. Okay, and then L is the max value. The graph of that function looks like this. So you start off with some initial population P naught, and it grows. And then at a certain point in here, this would be your exponential growth curve right here. And then at some point right here, this turns into slowing down, and it turns into what a log graph would look like. That's why it's called logistic growth. And then finally, it has a horizontal asymptote up here at the value L because it's never going to go past there no matter what. All right, so virus spread would be one example of something that would be modeled by the logistic model. All right, so example 4 is similar to that. Spread by skin-to-skin contact or via shared towels or clothing, methicillin-resistant Staphylococcus aureus, MRSA. I probably said that all incorrectly, but abbreviation is MRSA, can easily spread a staph infection through a university. Left unchecked, the number of cases of MRSA on a university campus T weeks after the first cases occur can be modeled by this logistic model. Okay, so they've given you what the model looks like. All right, we'd like to find the number of weeks of infected students after, or the number of infected students after 3 weeks, then after 40, and after 80. That just simply means plug in a 3, then a 40, then an 80 into your model. Find the rate at which the disease is spreading after 20 weeks. That's going to mean find a derivative of that function and then plug in 20. Explain why uninhibited growth models is inappropriate, but a logistic equation is appropriate for this situation, and then use a calculator to graph our equation. All right, so we're calculating the value at n equals 3 weeks, just plugging in 3 into our function that we were given in the problem. So if you plug in a 3, you should get 11.8. I would take a minute to maybe pause the video and do that on your calculator. So this would mean that about 12 students are infected after 3 weeks. If you plug 40 in for t into that model we were given, you should get 221.6, meaning about 222 students are affected after 40 weeks. And then after 80 weeks, you get 547.2, meaning about 547 students would be infected. All right, part B was to find the rate of growth, the rate of change, so we need a derivative. So this is a quotient rule along with our chain rule that involves the exponential. All right, so this is the bottom of that function times the derivative of the top, because remember that the top of that function was a constant, minus, then we have the derivative of the bottom, which is, they start off here, the top function, which was this constant, and then all of this part is the derivative of the bottom. So this was the bottom. So our derivative of 1 is 0, then you've got this whole function as it is, times the derivative of the power. So all these two things in parentheses represent the derivative of the bottom of the function, and that's what was on top, and then we divide by the denominator squared. So they've just cleaned this up a little bit in the numerator. Notice multiplying this function by 0 makes it cancel. So all they did here was take this negative 568.803 times this negative 0.092 to get this number, and then they've left this alone, and then went ahead and plugged in 20 for the t values on the calculator, and you should get 4.368. Meaning after 20 weeks, the disease is spreading through the campus at a rate of about 4 new cases per week. This can be a little bit tricky to evaluate on your calculator, so you will need to practice that and make sure that your answers are coming out correctly. If you have questions about that, just let me know and I can help you walk through how your calculator should be handling these, because every calculator is a little bit different. All right, part C was to explain why the uninhabited growth is not appropriate, but the logistic model would be. So unrestricted growth is inappropriate for modeling this situation because as more students become infected, there's fewer left to be infected. There's only a finite number of students on campus, right? That's what the L value would represent. The logistic equation displays rapid spread at the beginning, and then the growth slows down later. Remember how that graph kind of flattened out because it's growing slower because there's fewer students that are left to be newly infected. And then if you take that graph or that function that they gave us and graph it on your calculator, notice the scaling here in the horizontal direction, which is on your calculator, the X scale. If you set it to a window of like 0 to 100, and maybe ask it to scale by tens, and then set your Y window to go like from 0 maybe to 1,000 and maybe scale by hundreds, that will give you a more appropriate window to actually see this graph in. And it should resemble that shape. All right, so our summary of this section, 2 models. Uninhibited growth can be modeled by what we call a differential equation of the type dp over dt equals kp. In other words, the derivative of p with respect to t equals a constant times p. And the solutions to that are the p of t equals p naught, or initial value, times e to the kt. So when you have uninhibited growth, that's the model that we use. Certain kinds of limited growth can be modeled by what we call the logistic function. So p of t equals in this case, P of t would equal L plus CE to the negative KT. That's called limited growth. And in both cases, K and L have to be positive. Right? If you are ever in need of using either of these, this one, they will give you this. You should know how to create this. And on this one, you'll be given this form and just asked to do things with it. You don't have to memorize that. Right? So that is the end of section 2.4.